So today we are going to discuss about types of differential equation. So the differential equation can be broadly classified into two types. I written a differential equation in the D as D. Okay. So differential equation can be classified into two types. One is ordinary differential equation and another one is partial differential equation. I'll write the ordinary differential equation as ODE, okay, and the partial differential equation as PDE, okay. So the further this ordinary differential equation and partial differential equation can be further classified into homogeneous ordinary differential equation or inhomogeneous or non-homogeneous ordinary differential equation. Here inhomogeneous and non-homogeneous means the same, okay. Here also we have that same two types. So let's first look into ordinary differential equation. So the general form of ordinary differential equation can be written as I am taking a second order ordinary differential equation example, okay. So we have alpha d square x by dt square plus beta dx by dt plus gamma x, okay, gamma x equals to some function of t, okay. So this is a general second order ordinary differential equation. Second order because we have the highest order as 2, okay. This is the order of the equation, and it's an ordinary differential equation because we have only one dependent variable, okay. If we have two dependent variable, then it's called partial differential equation. Let's look about that in the later part of this video. So let's concentrate only on ordinary differential equation. So if there is only one dependent variable in the differential equation, then it's an ordinary differential equation. This is an example, and one of the physical example of ordinary differential equation is simple harmonic oscillator, okay. We can construct a simple harmonic oscillator from this general equation by particular choice of alpha, beta and gamma, okay. If we choose alpha equal to m, the mass of the system, beta equal to 0, that damping coefficient equal to 0, then gamma equal to k, the force constant, and f of t equal to 0. No, it's a free harmonic oscillator, okay, free simple harmonic oscillator. Then we end up with an equation which is of the form m d square x by dt square plus kx equal to 0. So this is an simple harmonic oscillator, okay. So what if the case we have beta not equal to 0, okay. Before looking at that, let me have another example of forced harmonic oscillator, okay. Forced harmonic oscillator. Here we can make this equation as d square x by dt square plus k by m x equals to 0, okay, and this k by m equals to omega square, where omega is the natural frequency of the harmonic oscillator, okay. So for forced harmonic oscillator, the equation, the parameters are alpha equal to m, beta equals to 0 and gamma equals to k, and here since it is a forced harmonic oscillator, we have f of t not equal to 0, and we take a function of the form f sin et, omega et, okay. Here the omega is the forcing frequency, and this e represents, it's an external, okay, external forcing frequency, okay. The forcing is coming from an external force, okay, forcing term, okay. So in that case we can write the above equation as m d square x by dt square plus kx equal to f sin e t omega e t. Okay, so now if you look at this equation, we have a t, we have a function which is a function of t, and t is the our independent variable. So this is an example of non-homogeneous equation, differential equation, and this is an example of homogeneous differential equation. Okay, so usually this whenever we use a forcing term, this is usually because to compensate the damping which is present in the system. So let me extend for an damped forced harmonic oscillator. Okay, so this is the equation for damped force harmonic oscillator. Okay, so for that we have a parameter choice, alpha equals to m, beta not equal to 0, gamma equals to k, and f of t equal to f sin omega e t or f cos omega e t. We can use any kind of forcing. So in that case we have an equation m d square x by dt square plus beta dx by dt plus gamma k x equals to f sin omega e t. Okay, so this is also an example of non-homogeneous differential equation, because we have a function which is a function of our independent variable, and this is an example of damped because we have a term, velocity term here, and it is a forced because we have a forcing term here, and it's a general harmonic oscillator equation. So whenever we have a differential equation with the velocity term, it is generally represented as damped one, and this beta is called the damping coefficient, because the frictional force is always proportional to the velocity. Okay, whenever we have a frictional force present in a system, then the frictional force increases when the velocity increases, and the frictional force decreases when the velocity decreases. We can see this from this example. So if we have a bath filled with viscous fluid, and if we drop a ball, and if this ball moves with high velocity, then it encounters a large frictional force. When if this ball moves with slow velocity, when it moves slowly, it encounters a less frictional force. Okay, so whenever we have a differential equation with a velocity term in that one, then it's a damped version of the differential equation, and this beta is called the damping coefficient. Okay, so this is also an example of non-homogeneous differential equation, because we have a function on the right hand side which is a function of independent variable. Here we don't have a function of independent variable, so it is called a homogeneous one. Okay, so let's look at the partial differential equation. Till now we look for ordinary differential equation. From now onwards we are going to look at partial differential equation. Okay, if one of the best example is our 1D heat equation, which is given as alpha dou square h by dou x square plus beta dou h by dou t equals to 0. Okay, so this is one of the example of one of the physical example for partial differential equation, and this is an homogeneous one because we don't have any function of our independent variable. So here the independent variables are x and t. Okay, so these are the independent variable, and our dependent variable is a function of both x and t. Okay, so whenever our differential equation, whenever in our differential equation if we have two independent variables, then the differential equation is called as a partial differential equation. Okay, and our dependent variable is also a function of both the independent variable. Okay, so here h represents the heat, so this is 1D heat equation. In a more general form, it is represented as dou h by dou t equal to some c times or alpha by beta times dou square h by dou x square. Okay, so this is 1D heat equation. So this is an example of homogeneous equation, since we do not have any functions of our independent variable x and t. So this is an example of homogeneous partial differential equation. Okay, so let's look at our another physical example, which is an non-homogeneous PDE. Okay, so one example is our famous Maxwell's equation. Our first Maxwell equation, del dot E vector equal to 1 by epsilon naught times rho of x comma y comma z. Okay, so this is an first order partial differential equation, and it's an inhomogeneous type. Okay, so if we expand it and write it, then we have dou ex by dou x plus dou ey by dou y plus dou ez by dou z equal to 1 by epsilon naught times rho of x comma y comma z. Okay, here we have three independent variables x, y and z, and our dependent variable e, which is a function of x, y and z. Okay, and in this side we have a function rho, which is a function of our independent variable. So this is an physical example of okay, example for non-homogeneous PDE. Okay, partial differential equation. So heat equation is an example for homogeneous partial differential equation, and Maxwell equation is an example for non-homogeneous partial differential equation. And this equations are example for homogeneous ordinary differential equation, and this damped force harmonic oscillator is an example for non-homogeneous ordinary differential equation. Okay, so this is the thing which I like to brief about the types of differential equation.